All right, guys, we're starting our last chapter today, and this one's kind of interesting. So what we're going to do is I'm going to combine 4 sections into 3 days for us to work on. None of the sections are actually really hard. It's just it all kind of blends together. So I'm just going to merge it all together, and we're just going to get it done in 3 days. All right, so let's start with some vocab. So these vocab words you're probably already familiar with. First one is power. A power is a product of repeated factors. Repeated factors. And then the base is the common factor. It's the number that's being repeated. And then the exponent indicates the number of times the base is repeated as a factor. So this diagram down here kind of explains. In this thing, we've got 1/2 as our base. It's the number that's being repeated. The exponent is 5. That tells us how many times it's going to be repeated, again, as a factor. Of course, we know factor means that we're going to multiply. And then the whole thing is called a power. Now, we've worked with exponents before, so this isn't new. But what we haven't done as much of is working with bases that are negative. What happens if we have a negative base that we're taking to the first power, second power, third power, so on and so forth? So we have this little chart here. It's got -3 as our base. And then it's got -3 to the first power, which means there's one -3. The answer is -3. -3 to the second power is -3 times -3, which is +9. Positive being the key word there. That's going to come back into play. And then for -3 to the third power, we've got -3 times -3 times -3. Well, 3 times 3 times 3 is 27, but there's 3 negatives, so it's -27. And then for the next one, we've got -3 times -3 times -3 times -3. And then so we have 27 is what 3 to the third is. Times that by 3 and you get 81. And because there's 4 negatives, that's even. They're all going to pair up and form a positive. So this pattern continues. I'm not going to fill in the whole chart because I don't have the copy and paste function here on my Explain Everything app, which I would totally just copy and paste and just add one more each time. But the idea is that when you're working with these negative bases, like -3, if you're raising it to an odd exponent, your answer is going to be negative. So -3, we had -27. This one's going to be negative as well for -3 to the 5th power. And then -3 to the 7th power will be negative. And then if you're raising it to an even power, your answer is going to be positive. And that's because since your base is negative, that exponent tells you how many negative numbers there will be. And we know that if you have an even number of negatives, your answer is positive. And if you have an odd number of negatives that you're multiplying, your answer is negative. So what's important to note here is if you have a base that is negative, make sure that you use parentheses. So we have to use parentheses when we have negative bases. The reason for that, I like to think of it as the exponents being nearsighted, right? If you write -2 and you put it in parentheses and raise it to the 3rd power, the exponent is going to see that negative because the parentheses act as a magnifying glass of sorts, right? So the negative will get repeated 3 times. I'm actually going to put parentheses around these so it doesn't get confusing. There we go. The negative will get repeated 3 times because the exponent sees the negative. However, if I were to write -2 to the 3rd power like this, the exponent, being nearsighted, is not going to see the negative sign because the parentheses aren't there. So what's going to happen is the negative will just remain there, and then you'll have 2 times 2 times 2. Now, both of these answers will give you the answer of -8. The one up here will give us -8 because there's 3 negatives. The one up here will give us -8 because there's only 1 negative. Either way, that number of negatives is odd. What's important to note, though, is if this were a positive exponent, there'd be another negative here, and then all of a sudden this would be +16. And if this was to the 4th power, there'd be another 2 here, but there'd still just be that 1 negative, so it'd be -16. So it does really matter if the negative is in parentheses or not, because if the parentheses aren't there, then the base is just 2. But if the parentheses are there, then the base would be -2. Okay, so let's look at this first example here. -7 times -7 times -7. Write each product using exponents. This would be -7 to the third. Notice how I put the parentheses because there's a negative base. For example B, we have pi repeating 3 times, pi to the third, and then we have r repeating twice, so times r squared. For example C, now this is a fraction, and typically you'll see fractions put in parentheses too, and the reason for that is because remember when you multiply a fraction by an exponent, just like when we did square roots, like the last chapter when we had the square root of 1/9, we know that we were supposed to square root the top and square root the bottom to get 1/3. Well, it works very similarly for exponents here. I know that 1/4 raised to the 5th power, if I use parentheses like that, means I'm going to multiply the numerator by 5 and then the denominator by 5, or not by 5, the numerator times itself 5 times, and then raise the denominator to the 5th power as well. And then the last one here, D, we've got 0.3, and that's raised to the 4th power. You can choose to put parentheses around that if you want to. You don't really have to there because it's not negative. And then we've got x to the 2nd power. Now, for these examples, you'll notice it changed the directions here. Now it says evaluate. That means we actually want to solve and see what it is. So in the first one, they've given us -2 to the 4th power. And as we already mentioned, there's parentheses here, so we know the base is -2. That means the negative is going to get repeated as well, not just the 2. So it'll be -2 times -2 times -2 times -2, which is positive 16. Okay, that's actually the example I used on the last page. For example B, the exponent's the same, but the base is now just 2. It's not -2 because they didn't write parentheses around it. So what we have here is we have a negative that's just basically dropping down. Let me try that again. The negative is dropping down, and then we're going to repeat the 2 4 times to get 16. So the negative just kind of drops down because it didn't get repeated. So we have -16 for part B. For example C, the negative is being repeated, but it's being repeated 5 times. So it's still going to be negative, -32. And then for D, the negative is not being repeated. It's just going to drop down, and the 2 is being repeated 5 times to get 32. So for these two, we just happen to get the same one anyways, because whether we have 5 negatives or just 1 negative, either way, that's still odd. So it really just matters if that exponent's positive. Right? If you have a positive exponent, then, I'm sorry, not positive, an even exponent. If you have an even exponent, then it's going to result in possibly 2 different answers, depending on if those parentheses are there or not. All right, and just some order of operations review here. Remember, exponents follow parentheses in the order of operations. Please excuse my dear Aunt Sally. So I'm going to do 3 to the 4th first, and 3 times 3 times 3 times 3 is 81, because that's the same as 9 times 9. And then multiplication comes before addition. So we have 3 plus 162. And then finally, the addition step is going to give us 165. For example B, we've got -1/6 being repeated 3 times. So now it's in parentheses, so it's a negative base, and it's being repeated 3 times. And since 3 is odd, it's still going to be negative, right? Negative, 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 still negative. And then that's going to be 1 to the 3rd power and 6 to the 3rd power. Well, 1 to the 3rd power is just 1, and 6 to the 3rd power, 6 times 6, 36, times 6 is 216. Next one here, the absolute value of -3 divided by 27. Well, -3 divided by 27 can be written as a fraction, -3 divided by 27, which actually would reduce to 1/9. And since we have absolute value symbols, our answer has to be positive. So even though there's a negative there, we would still just get 1/9. And then for example D, we've got 9 minus 5 to the 4th times 0.5. So 5 to the 4th is 5 times 5 times 5 times 5, or 25 times 25, which is 625 times 0.5. I have to do the multiplication before I do the subtraction. All right, so 9 minus, and then 625 times 0.05 is 312.5. So we're going to get an extremely negative number here. And then 9 minus 312.5. And that's going to give us -303.5. 0.5 is our final answer. All right, this one's going to take us back to our Chapter 8 volume chapter. It says, in sphering, which I didn't know was a thing, but apparently it is. It says a person is secured inside a small, hollow sphere that is surrounded by a larger sphere. The space between the spheres is inflated with air. This just looks like a lot of fun. Obviously, they're rolling down a hill. What is the volume of the inflated sphere? Write your answer in terms of pi. All right, correction here. It says, what's the volume of the inflated space? So basically what we're finding is how much space is there between the two spheres, the inner sphere and the outer sphere. So what we're going to do is find the volume of the inner sphere, find the volume of the outer sphere, and as you'd expect, we just subtract them and see how much space is left. So we're going to need to know the volume formula for a sphere, and that is 4/3 pi r cubed. Maybe you remember that from earlier in the year. So 4/3 pi, and then the radius of the inner sphere, you can see the diameter of the inner sphere is 2, so the radius would be 1. And 1 cubed, right? So it says write your answer in terms of pi. So 1 cubed is 1 times 4/3 is just 4/3 pi. That's the volume of the inner sphere. Now for the outer sphere, same formula, 4/3 pi r cubed. But this time the radius is going to be 1.5 because the diameter is 3. That makes the radius 1.5. I'm actually going to write that as 3 halves. 1.5 would be 3 halves because I've already got a fraction there with the 4/3. 3 halves to the third power. 3 to the third power is 27, and 2 to the third power is 8. So remember, I'm just taking both these to the third power then. And then now I can cancel. I'm multiplying everything here. So the 4 and the 8 can cancel. And then the 3 and the 27 can cancel. So I get 9 halves pi. Now it's time to subtract, and we're going to subtract away the outer sphere, 9 halves pi, from the inner sphere, 4/3 pi. We need a common denominator, and that common denominator is going to be 6. So I'm going to multiply by 3 to get 27 over 6 pi, minus, and then multiply both top and bottom by 2 to get 8/6 pi. 27 minus 8 is 19/6 pi, which is my answer. Although if it makes more sense, you might want to convert that into a mixed number. 6 goes into 19 3 times with 1 left over, so 3 and 1/6 pi. And since we're talking about volume, we're going to be talking about cubic meters, so meters cubed. All right, now it's time to get into the new stuff, the real new stuff, the power properties. And so we have 4 different properties that we're going to talk about. And the first one's called the product property, or the product of powers property. And so what it says is that anytime you are multiplying 2 powers together with the same base, all you have to do is add the exponents, and I'm going to show you why. 2 squared means 2 times 2 times 2 to the 4th power means 2 times 2 times 2 times 2. Well, that's all just multiplication, and there's 6 2's, so 2 to the 6th power. So all I had to do was add the exponents together. And that's what this says. To multiply powers with the same base, that's important. You can't do this if they have different bases. If this was a 2 and this was a 3, you wouldn't be able to do this. But if they have the same base, you can just add their exponents together. And that's what this m plus n is that's down there. They're just adding the exponents. In this next one, the base is -3. So I would have -3 times -3 times -3 times -3 times -3 times -3. And so altogether, I've got 6 of those -3's. -3 to the 6th power. Make sure you use parentheses because there is a negative base. So 3 plus 3 gives us 6. Now with this next one, x times x times x times x times x times x, and then there's only one more x. So altogether you get 7, and if you're wondering how that works, it's because this should be a 1 right there. It's not written because it's kind of implied. If it's just x to the 1st power, it's x. But if you're ever given a number or a variable that has no exponent, it's just to the 1st power. So 6 plus 1 is 7. I'm not even going to write this next one out. I've got 5 plus 2 is 7, so this will be 10 to the 7th. And that is the product of powers property. Pretty simple. Now, if there's a product of powers property, you better believe there's a quotient of powers property, and that's very similar. We're just going to do the exact opposite of what we did last time. So I'm going to write this repeated multiplication out, 2 times 2 times 2 times 2 over 2 times 2. And what's going to happen is you're going to see these 2's cancel and those 2's cancel because you're dividing, right? And then you're left with 2 2's on the top, so 2 to the second power. Notice how it says write it as a power. I mean, I know that's equal to 4, but it wants me to write it as a power. For the next one, I've got 7 y's on top. That's a lot of y's. 1, 2, 3, 4, 5, 6, 7. And we've got 3 on the bottom. And so we've got these 3 canceling out those 3, leaving us with 4 on the top, y to the 4th power. And so all I'm doing, if you didn't figure it out, is I'm subtracting the exponents. 4 minus 2 gives us 2. In this one, 7 minus 3 gives us 4, y to the 4th. I'm not going to write out this next one. 6 minus 1 will give us 5, 5 to the 5th. Now, they didn't have to write that exponent as a 1. It's implied. So if you do see that, just know you're still subtracting 1. And then the last one, a to the 10th over a to the 9th is the same as a to the 10 minus 9, if I'm going to write it like how they did right down here. And 10 minus 9 is 1. So a to the 1st power, or I could just say a, because remember, if it's a to the 1st power, it's still just a. Now, what's important here is that you can't have a equal to 0. That can't happen. And the reason is because if your base is 0, well, 0 raised to any power is just 0, right? So it kind of doesn't follow these rules. So we have to make sure we actually have a number other than 0 as our base. And this is the quotient of powers property. You're just subtracting the exponents if your bases are the same. This next one's maybe my favorite one. It's the power of a power property. It just sounds weird to even say. Power of a power property. So let's figure out what this means. X squared is being raised to the 4th power. So that means I have 4 of those x squareds. Now, we know from the product property that if I'm multiplying with the same base, I would just add the 2's all together. So that should be x to the 8th power. And you can prove that because x times 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 x is a total of 8 x's. But what I have to do, the shortcut here, is all I have to do is multiply the exponents together. So the key difference here is that the power x squared is being raised to the 4th power. It wasn't being multiplied by x to the 4th. It was being raised to the 4th power. So if you have a power being raised, or as they say, a power of a power, then you just multiply the exponents m times n. So this next one, we've got 5 to the 1st power, or just 5, right, to the 3rd. Well, that's easy. 5 to the 3rd. 1 times 3 is 3. The next one, 6 to the 3rd times itself, another 6 to the 3rd, is going to give us 6 to the 6th. You can get that by adding 3 and 3, or just doing 3 times 2, which is the simple way to do it. And this last one I'm not even going to write out. 5 times 3 is 15, b to the 15th power. Pretty simple. That's the power of a power property. You multiply the exponents together when you're raising a power to a power. The last one is called the power of a product property. This one's maybe the most confusing. It's not very confusing, but basically what we have here is we have a product inside the parentheses, and you're raising the entire thing to the 3rd power. So what we're going to do, I like to think of it as distributing the exponent to both of these numbers. So this would be 2 times 2 times 2, and then this would be 3 times 3 times 3. And so that's really just going to give us 2 to the 3rd power times 3 to the 3rd power. Now, I could totally evaluate that, right? I could say 2 times 2 times 2 is 8, times 3 times 3 times 3 is 27, but it doesn't say to evaluate this one. It just wants us to write it as a power. So 2 to the 3rd times 3 to the 3rd. Another way I could evaluate it is I could have said, well, 2 times 3 is just 6, and 6 to the 3rd power, 6 to the 3rd power is actually going to give us the same answer, 216, that 8 times 27 will give us. But again, just writing as a power. So with that being said, the next one's going to be 2 to the 2nd times 5 to the 2nd. You're just basically distributing that power to each of those numbers, just like they did in this example here. And then finally, okay, so this one I can't simplify, right? I could make 2 times 5, 10. But the one down here I can't simplify, so this is where it's really important that you know the rule. I have to distribute the 4 and distribute the 4 there. So this is 6 to the 4th times a to the 4th. And then the final one, I'm distributing the exponent of 2, so 3 squared x squared. And this is the power of a product property. So if you have more than one base in the parentheses that you're raising to a power, you just treat the exponent like it's working on both numbers, right? You have to distribute just like you see down here, right? Both numbers inside the parentheses get raised to whatever power that is. All right, so I have a ton of examples for us to look at because this is new, let's face it. It's also not very hard. These won't take us very long to do. Just one of those things you got to practice or see done a few times, then you get the hang of it. It says simplify the expression. Write your answer as a power. So because I'm writing my answer as a power, I'm not going to evaluate, right? I don't want to actually solve. I'm just writing as a power. So 2 to the 4th times 2 to the 5th. This is the product property that says you can just add these exponents together to get 2 to the 9th. For b, same thing. I'm going to, since it's the same base, I'm going to use my parentheses because it's a negative base, and I'm going to add the 3 and the 6 together to get 9. So negative 1/2 repeats 3 times, then it repeats 6 more times. It's repeating a total of 9 times. For example, c, just put a little 1 right there. I've got z to the 13th power. And then for example, D, now we switch and start using the quotient property, which says if you're dividing these powers, have the same base, you subtract the exponents. So 9 to the 7 minus 4 would be 9 to the 3rd power. I'm just subtracting the exponents. Here, for example, E, 7 minus 6 is 1. H to the 1st, or that's just the same as H. And then, for example, F, 9 minus 3 is 6, so negative 7 to the 6th. Notice again how I'm using parentheses, because if you write negative 7 to the 6th like this is wrong, because that's going to give you a negative answer, whereas this one will give you a positive answer because of the even exponent. So I included a couple study tips here. When a number is written without an exponent, the exponent's 1. We went over that, right? So this was a 1 up here. And then for the next one, when dividing powers, do not divide the bases. You're just subtracting the exponents. A common mistake that you'll see is some students will just do 2 divided by 2 is 1. And that's not what we do, right? All we're doing is we're keeping that same base, and then we're subtracting 6 minus 4 to get 2 for the exponent. So don't make those mistakes. Starting with example G, we're going to use the power of a power property, which says we're going to do y to the 2nd power, all raised to the 4th power. So I'm going to just multiply those exponents together to get y to the 8th power. And that makes sense, because if you think about it, y squared times y squared times y squared times y squared, there's a total of 8 y's. So it just makes sense if you think about it. For example, H, I've got 4 and 5 as my exponents. I'm raising w to the 4th 5 times, right, to the 5th power there. So that's going to be w to the 20th. And then for I, this is, I've got 2 numbers. This is the product of a power property, or power of a product property, I should say. So I'm going to distribute the 4, and I'm going to distribute the 4 there. And so because the instructions told us to simplify, I'm actually going to take this 5 to the 4th, and I'm going to give us an answer. 5 to the 4th is 625. But I can't do that with the y, right? Y is just going to remain as y to the 4th because I don't know what y is. So I'll just call this 625 y to the 4th. And then here I don't even have a number, so I can't even simplify any farther. This is going to be a squared to the 3rd power. Now, I'll write that out because that's kind of confusing. A squared to the 3rd power times b to the 3rd power. So when I distribute, it's not only that 3 just gets tacked on, but if there's already an exponent there, the other property rules kick in. If I'm raising a to the 3rd, or a to the 2nd power to the 3rd power, that's actually a to the 6th power, because the power of a power property says I just multiply those. And then b to the 3rd is my other one there. So a to the 6th times b cubed. All right, now we're going to crank it up a notch with a few more challenging examples here. So for k, again, I've got several things in the parentheses. Each one of these is going to get raised to the 2nd power. So I've got negative 1/3 being raised to the 2nd power, which, by the way, that's going to give us positive 1/9. And then I've got m being raised to the second power, and then n being raised to the second power. So my final answer is positive 1/9 m squared n squared. For L, I've got the quotient property I'm going to use here, but there's a lot of 3's. A couple different ways I could do this. Maybe the easiest way is just to go ahead and simplify the top and make that 3 to the 6th over 3 to the 3rd. And then after I add these two exponents to get 6, now I can subtract the 3 from the bottom, and that's going to give us 3 to the 3rd power. That's one way you could do it. Or you could immediately take these 3 3's, cancel them out with 3 of these, leaving you just 1 3 there, plus the 2 exponent gives you 3. So again, a couple different ways you could think about it. Your brains are all different, and you'll find a way that works best for you. For example M, we've got same type of problem here. We've got 2 to the 8th power on bottom and 2 to the 15th power on top, and I can now just subtract those to get 2 to the 7th power. And then for N, I could multiply across the top, multiply across the bottom, or I could simplify each of them first. I guess I could try that and just be new. And so I could simplify this fraction and make it 5 to the 5th power after I subtract. That's what the quotient property says. I could just subtract those. And then 5 minus 2 is 3. And then now I can multiply. And because they're the same base, I just add those exponents to get 5 to the 8th power. And then example O. Example O, last time I simplified each of them. This time I'm just going to multiply across. A to the 10th times a to the 7th. I'm going to add those exponents to get a to the 17th. Remember, I'm not multiplying those exponents because I know it says multiply, but the only time I multiply the exponents together is if I'm raising a power to a power. That's the only time I multiply. Otherwise, I'm just going to add those exponents to get 17. And then that's going to be over 6 plus 4 is 10, a to the 10th power. And then now I can subtract these because of the quotient property, and that's going to give me a to the 7th power. This next example, it's nice to get a story problem in here every once in a while. This next example says a gigabyte of computer storage space is 2 to the 30th bytes. Maybe some of you are more familiar with this than I am. The details of a computer are shown. How many bytes of total storage space does the computer have? It says the total space the computer has, total storage space, is 64 gigabytes. So I need to find out, since each gigabyte, and there's 64 of them, since each gigabyte is 2 to the 30th bytes, what is that? And so the hint is write 64 as a power. Well, there's a lot of different ways I could do that. 64 is 8 squared, right? That's not going to help me, though, because those have different bases. What if I thought of 64 as 2 to the 6th power? 2 times 2 times 2 times 2 times 2 times 2 is 64. Now, what I could do, since I have the same base, now I couldn't have done this if I would have done it to the 8th, or made my base 8 because they have different bases, but now that they have the same base, those property rules kick in, and this is going to be 2 to the 36th bytes. B-Y-T-E-S. There we go. Next one says the projected population of Tennessee in 2030 is about 5 times 5.9 to the 8th. Predict the average number of people per square mile. Well, if I'm doing it per square mile means I need to do people per or over miles, square miles. So the number of people we know is 5 times 5.9 to the 8th over the number of square miles is right here, 5.9 to the 6th. So could type this in my calculator, but heck, this is going to save me a ton of time. These 6 are going to cancel out with 6 of these, and 8 minus 6 is 2. So now I just have 5 times 5.9 to the 2nd power. Again, using that quotient property, I was able to simplify 5.9 to the 8th and over 5.9 to the 6th just to 5.9 squared. So 5.9 squared is 34.81, and then I'm going to times that by 5 to get my final answer, and that's going to give us 174.05, and that's people per square mile. So that's about how many people would live in each square mile of Tennessee, and that's in 2030. Let's look at some more geometry problems, because we know a lot of our geometry problems use exponents anyways. And so even though I could solve this problem without using my properties, I'm going to show you how the properties could be used here. It says find the volume of the smaller cube, how many of the smaller cubes will fit inside the larger cube. And so we're going to fill this table down here to help us with that. And so the volume of the smaller cube would be 3 times 3 times 3, or 3 to the third. The volume of the larger cube would be 3 squared. And then again, length times width times height means I multiply that by 3. Every time you're cubing a number, you're raising it to the third power. So here I'm cubing 3 as my side. And then for the bigger one, I'm cubing 3 squared, which of course we know is 9, but I'm just going to hold off on turning those into whole numbers just yet. So the larger volume would be 3 to the 6th power over the smaller volume, 3 to the 3rd power. And that's going to give us 3 to the 3rd power, which is 27. So 27 of these guys would fit inside that larger cube. Now for the tannish looking cube, I've got the side of 10, that's going to be raised to the 3rd power. And then for the bigger cube, the volume would, the side is 10 squared, so the volume is going to be 10 squared raised to the 3rd power. That's going to give me 10 to the 6th over 10 to the 3rd, which is 10 to the 3rd, which is 1,000. So 1,000 of these little cubes could fit inside that big cube. All right, our final topic from this part of chapter 10, the exponents part, is negative and zero exponents. Yes, they do exist. You can have zero and negative exponents, and the way they work is if you have zero exponent, you're just looking at the ones column. So again, if I had the number 3,452.867, that was my number. The 3 is in the thousandths column, which is 10 to the 3rd. The 4 is in the hundredths column, 10 squared. The tenths is in the ones column, or the 5 is in the tenths column, which is 10 to the 1st. And the 2 is in the ones column, and since there aren't any zeros in the 1, that would be 10 to the 0 power. So one of the things we'll talk about, like I said, is the zero exponent. And then we just keep going. This would be 10 to the negative 1st power. That's your tenths columns. 10 to the negative 2nd is your hundredths. And 10 to the negative 3rd is your thousandths. And this pattern just keeps going in both directions. So let's look at a couple problems that involve some of the properties we've already used. This one's the quotient property. 5 to the 3rd divided by 5 to the 3rd. I just subtract those. I get 5 to the 0. Now, 5 to the 0 actually is just 1. And the reason for that is because I'm dividing the number on top is the same as the number on bottom. Think about what would happen if you divided 4 divided by 4, or 5 divided by 5, or 6 divided by 6. If you divide a number by itself, you always get 1. So if your exponent is 0, that's actually going to give us 1. So anything except 0 to the 0 power is 1. Again, 2 minus 2, 6 to the 0 is just 1. Because I'm dividing the number by itself, it goes into itself exactly 1 time. Now, if I use the product property, instead of subtracting the exponents, I would add the exponents. Well, 3 to the 0 times 3 to the 4th is just 3 to the 4th, right? Like this 3 to the 0 is just 1. So 1 times anything is just itself. 8 to the 0 power is just 1, as we mentioned before. So 8 squared times 1 is just 8 squared. So again, anything to the 0 power except the base of 0, which we've kind of talked about, but any other number raised to the 0 power is actually just 1. A couple more examples here. I've got negative 3 and positive 3. I'm going to add them together to get 0. 5 to the 0 we just said is 1. And then again here, 2 and negative 2. The product of a power property says I would just add those. 2 and negative 2, when you add them, give you 0. And so that's going to give me 6 to the 0 power, which again is just 1. So you must reduce it to 1. Right? You can't leave it as 6 to the 0 power. You have to go ahead and say that's 1. All right, so here are the rules then, zero exponents and negative exponents. For any non-zero number, so the base can't be 0, if you do 0, or if you raise that number to the 0 power, your answer is always 1. And then, like I said, you can't raise 0 to the 0 power. That's actually undefined. It just doesn't exist. And then here's a couple examples. 4 to the 0 is 1. Any variable raised to the 0 power is also 1. And then with negative exponents, we haven't talked about negative exponents, but we're going to look at them right now. Negative exponents. Here's what negative exponents do. For any integer n and any non-zero number a, where a to the negative n exists, to find a to the negative n, you take the reciprocal of a to the n. Now that seems kind of confusing, so let's just look at the example they did right there. 4 to the negative second power means the negative does not make the answer negative. What it does is it drops the 4 to the bottom of the fraction. So 1 over 4 to the positive second. A to the negative n is 1 over a to the positive n, and that's what it means by reciprocal right up here. You're flipping it. If it's on the top, it goes to the bottom. If it's on the bottom, it goes to the top. And the reason for that, if you remember that chart we were just looking at when we had the 10 to the negative first power, 10 to the negative second power, we said this was tenths. We said this one was hundredths, which I can't even fit that on the screen. So that would be 1 over 10 to the first power, which is just 10. And this would be 1 over 10 to the second power, which is 100. So a hundredth, a tenth. It just makes sense. So this one says evaluate. We're not going to leave it as a power. We're actually going to write the answer. 3 to the negative fourth is 1 over 3 to the fourth, which is 1 over, and then 3 squared is 9, and 3 squared is 9, so this would be 81. Now this is extremely important. You need to write your answers as fractions. I know that some of you are tempted just to type this into your calculator and get a decimal, which we know 1 over 81 would not be a very nice decimal anyways. On your test, you are going to be required to write these as fractions so that I know that you know what the rules are, that you're not just typing into your calculator because you don't know what you're doing. So in this example B, we've got, we're dividing, so we're going to do 6 minus 7. It's a negative base, so I have to put it in parentheses. 6 minus 7 is negative 1, and then I'm going to write that using a positive exponent as negative 3 over, or sorry, the 1 over, I forgot to say 1 over negative 3 to the first power. So negative 3 to the negative first means 1 over negative 3 to the positive first, and then 1 over negative 3 to the positive first is just 1 over 3, and then the whole thing's negative. So it's not the negative exponent that made it negative, it was the negative base that made it a negative, and I still have an odd exponent, so it's still going to be negative. It's just that negative 3 to the first is the same as 3. Let's look at that one. Might have been a little confusing. Let's look at the next one. This might clear things up a little bit. Negative 2 to the negative fifth power means 1 over negative 2 to the positive fifth power. So I still have to figure out what that is. I know that I've got 1 on top, and then negative 2 times negative 2. Now this is a negative base. It's in parentheses, so I'm going to repeat it 5 times. So the answer is going to be, let's scratch this out. The answer is going to be negative because it's an odd exponent, and 2 to the fifth power is 32. So negative 1 over 32. Remember, we're writing our answers as fractions, not as decimals. For example D, we've got the product property kicking in here. 1 times 1 is 1 on the top. And then on the bottom, 7 and negative 4 makes 3. Just like that. And I'm going to go ahead and evaluate that. 5 times 5 times 5 is 125, so 1/125th. For example E, we've got on the top, this is going to give us 4, and then 5 plus negative 3 is 4 squared. There. And then 4 squared on bottom. That's going to give us, when we subtract, 4 to the 0 power. And just remember, when anything to the 0 power has to reduce all the way down to 1. 4 to the 0 power is just 1. And then the last one here, I've got 1 on top. I've got 2 to the first power. Just go ahead and write that 1 there. Times 2 to the negative fourth. So I'm multiplying, so I have to add 1 and negative 4 makes negative 3. Now, what's interesting here is that if you have a negative exponent and it's already on bottom, what would the reciprocal do? Well, it's going to reverse it and write it on top. So this becomes 2 to the positive third power over 1. That's what the reciprocal would be. That's what negative exponents do. It's just that I don't need to write it over 1 because anything divided by 1 is just itself. So 2 to the third divided by 1 is 2 to the third, and 2 to the third actually equals 8. All right, let's do some more reviewing with some examples mixing in everything we've gone over so far. This one says, simplify, write each expression only using positive exponents. Positive exponents. No negative exponents allowed. No zero exponents allowed. We can only write our answer using positive exponents. So -5 to the 0 power, well, too bad. You're going to be 1 because I can't leave you as a 0 power because I need positive exponents. So you're just going to be 1. Anything to the 0 power is 1. The next one, I've got 9 on top, and then let's look at these y's. These 3 y's, -3, they're all going to move to the bottom because it's a negative exponent. The negative exponent is not going to make my answer negative, but it is going to take those 3 y's on the top, and it's going to move them to the bottom of the fraction and give me y to the 8th on the bottom. For the next one, I could add these together. 0 plus -10 is still -10. Or you could have just said, oh, b to the 0, that's just 1. Nothing happens. And then because I have to write my answer using positive, oops, there we go, positive exponents, I need to make this 1 over b to the 10th. I need to write the reciprocal of that. For example D, the 8 stays right where it's at. The -2 is only affecting the x. Think of this as 8 to the 1, 8 to the first power. So it's only the x that's going to move. X squared is going to move to the bottom. It's not the 8 that's going to move to the bottom. It's just the x because the 8 already has an exponent. Its exponent is 1. All right, next one, we've got the 15 is on bottom. It's going to stay on bottom. And then I've got these 6 z's are going to cancel out with 6 of the z's on bottom, leaving me just 3 z's on bottom. Now that means there's nothing on top. Well, what happens if your fraction reduces down to where there's nothing on top? You just put a 1. So we have 1 over 15z to the 3rd. Next one here, I'm going to use the power of a power property. I'm going to multiply these together to get c to the -15th. And c to the -15th is equal to 1 over c to the +15th. For example, z, we are going to raise 10 to the 2nd to the -8th power. And so we're going to multiply, because we're raising a power to a power. 2 times -18 is -16. I don't know if you can see that very well. Maybe I should stop using that color. 10 to -16th. And that's going to be 1 over 10 to the +16th. And again, I'm not going to evaluate that. I'm just going to write it as a power with a positive exponent. And then the last one here, it says be careful. What's so tricky about this? Well, the negative is in the parentheses, right? So I know that anything to the 0 power is 1, but there's a negative in front of this. So this is actually equal to -1 being raised to the -3rd power. And so that's going to be 1 over -1 to the +3rd power, and 1 over, and then -1 to the 3rd power is -1 times -1 times -1, which is still -1, and then ultimately 1 over -1 is -1. That one was longer than probably any of them that you'll have in your homework. Just a lot of different steps in there, but this is going to give us -1 for H. In the last problem here, it says a drop of water leaks from a faucet every second. How many liters of water leak from the faucet in 1 hour? What does it say down here? It says drops of water. Every drop of water is 50 to the -2 liters. And so every second, one of these drops is leaking. Okay? So it says how many liters of water would leak in 1 hour? Well, in 1 hour, how many seconds is that? I have to turn this into seconds since it says it leaks every second. So in an hour, you have 60 minutes. And every minute has 60 seconds. So I've got 60 squared, right? So 50 to the -2nd power times 60 squared, because that's how many seconds are in an hour. Now I cannot add these together because they're not the same base. So I have to treat them separately. This would be 1 over 50 squared times 60 squared. 50 squared is 2,500. And then 60 squared is 3,600. So if I cancel and cancel, that's going to give me 36 over 25. And I will write this answer as a decimal. And it's 1.44 liters. 1.44, so not quite 1.5 liters every hour are leaking from this faucet?